So this is the slide where I want to show what is meant by the angular resolution. So low L is the low angular resolution, and high L is meant to give you better angular resolution. So you're looking at the final structure. And when the peak is right here, then you see the structure being rather prominent. So that's the idea of this animation. So just give you a sense of what is this, the L is meant to actually be. And this is how the power spectrum changes as a function of the curvature. So I mentioned that location of this peak reflects this inner angle of this big triangle, where one of the edge is the size of the sound horizon. The two other edges are basically the distance to the last scattering surface, namely 13.8 billion light years. So if you change the curvature, then this peak shifts left and right. So that's what I mentioned yesterday. Now you see this in action in how this actually affects the power spectrum of cosmic microwave background. And this is the dark matter, which gives you the basic depth of the gravitational potential, and that gets reflected in overall amplitude. So that's what you're seeing here. So depending on how much dark matter there is, that's the amplitude changes. And this one you probably have seen, I don't know. So this relative size of the odd and even peaks changes by changing the content in baryons, we call, or basically atoms and electrons. So that's the animation I couldn't show yesterday. So anyway, so that's now done. And let me get back to inflation. And in addition to inflation, I'm going to talk about other potential sources of gravitational wave from early universe. So we were talking about the fact that the microscopic universe during the inflation has the uncertainty principle that every energy density fluctuates because of a small size of the volume. And that mathematically gets reflected in this expression here, that when this field starts to roll down the potential, you solve the classical equation of motion for it, but on top of the classical solution equation, then you actually put this quantum fluctuation on top of that. So because this height of the potential is basically the constant energy density during the inflation, so the height of the potential due to fluctuation changes from one place to another by derivative of the potential times the amplitude of fluctuation, h over 2 pi. So that's this combination of v prime times h over 2 pi. So that's delta rho. And you divide it by rho, but for a reason of making sure that the quantity is actually invariant and the general coordinate transformation, the combination that should come downstairs turns out to be the energy density plus pressure. And if you add both of them in, they actually nearly cancel. And what's left is this sort of kinetic energy part of the energy density. So that's what comes downstairs. So this combination is then the quantum fluctuation of the overall energy density. And that's what gets reflected in the picture of the Big Bang I showed you yesterday, namely the map of the temperature in cosmic microwave background. So the idea of inflation is to really produce this kind of the fluctuation in density and temperature. And overall, everywhere is basically the same because they started out from the same place, basically, covering the entire universe we see today. That's why the different parts of the universe have the same temperature. But on top of making the totally homogeneous isotropic, you also implant this a little bit of the fluctuation. And that, what we think, is the source of all the structure in the universe today, stars, galaxies, and even us. So that's the way it is supposed to work. So that's the picture. So this fluctuation temperature is supposed to have come from the quantum fluctuation. And so this is really, crazy story, right? We think the universe started out with a size much smaller than the size of an atomic nucleus. Everything was supposed to be in there. And because of the small size of the universe, you have this quantum fluctuation. And the quantum fluctuation is, in the end, the way we came from. So it's a really sort of mind-boggling, crazy idea, but it works. I'm going to show you some data on this. But anyway, so I showed you this video too, so let me skip that. And so the idea then is that you start out with density fluctuation, which is only at the level of 10 to the minus 5. So it's a tiny fluctuation, but because of the gravitational pull, the parts of the universe, which is a little bit dense compared to the rest, has more stuff in it, so that gravitational pull will actually bring more stuff into the same region, becomes denser, and pull more stuff in and so on and so forth. And that's how eventually this seed for the structure grows to the level of forming stars and galaxies. So starting from 10 to the minus 5, you achieve something like 10 to the plus 5. And that's what the role the gravity plays. So once the quantum fluctuation is there, the seeds have been planted, and the rest of the job is done by gravitational pull. But you need a source of gravity too. And the source of gravity is actually dark matter. And I mentioned already that we don't know what dark matter is, but it's a dominant form of matter in the universe. So what is actually pulling stuff together to form this structure we see today is the gravity by dark matter, not the ordinary matter. So that's actually a very important point. And here's a computer simulation of how structure evolved. Starting from this initial condition where you have the fluctuation only at the level 10 to the minus 5, there is still a little bit of the density contrast here and there, and the slightly more dense part has more dark matter in it. And gravitational pull by the dark matter pulls more dark matter in there, becomes denser, then the gravity becomes stronger and pulls more stuff in, become even more denser, even more strong gravity, and so on and so forth. At the end of the day, you see this contrast growing. And where the dark matter is very dense, eventually the ordinary matter, namely atoms, a gas of atoms get pulled in, and they scatter against each other, emit light, and cools down, and eventually collapses to stars and galaxies and us. And what you see on the left pane of this animation is the hypothetical universe that does not have dark matter. And so even after 13.8 billion years, then the contrast doesn't grow. There's not enough gravity because of the absence of dark matter. And in that kind of a universe, basically, we wouldn't exist. So the idea is that the inflation sowed seeds of the fluctuation, and dark matter nurtured and grew them. So the way I had to put it in the case of, for example, if I was giving a public lecture, is this phrase, inflation is dad, that he planted all the seeds. And dark matter is mom, who nurtured the seeds and had make sure that they will grow to a full-fledged stars and galaxies. So that's the sort of a main message of modern cosmology. So the question is whether this really makes sense. So if the fluctuation, what's that?
Yeah, can I ask something about so the density fluctuation is not smeared by the thermalization. So when the thermalization happens, it's already causally disconnected. That's why the seed remains.
That's correct. That's correct. Yeah. So because the light travels with a finite speed, the speed of light, at any moment in the early universe, only a finite size of the universe can be connected to each other. So even if there's dense part and sparse part, and they may want to equalize with each other, but if the distance is too large, then causality prohibits from that happening. So basically the fluctuation of density is frozen for a long period of time. So this is what is called the super horizon size fluctuation. Because inflation stretched the initial size of fluctuation to incredible distance, then this cannot equalize because they're just too far away from each other, and hence super horizon fluctuation. Yeah, that's right. So thank you for asking the question. Okay. So the question is whether it really makes sense from the point of view of the data. So if the fluctuation comes from this quantum nature of this the scalar field that rolls down the hill, you actually expect, at least in simplest theories, the fluctuation to be more or less Gaussian. And what you can do is to take this map of temperature from cosmic microwave background, and then you just create a histogram of how many patches of the sky have certain temperature. And then you can see if the fluctuation is really Gaussian. And indeed, it does look like a beautiful Gaussian. So this is one of the evidences that the origin of this fluctuation to be quantum fluctuation seems to bear out and be consistent with the data. And it turns out that there was a question about it yesterday. If you think of somewhat more complicated models of inflation, which may have, for example, not just one field, but 2 or 3 extra fields that causes inflation, then you have many different directions that fields can fluctuate. Then the fluctuation may not be Gaussian. So that's the way you can start testing what kind of inflation seems to be consistent with the data. So not only that this idea seems to support inflation, it actually supports rather the simplest kinds of inflationary models. And people came up with all sort of models of inflation, but it seems to prefer really the simplest kind. And that's what data seems to suggest. And also that, as I talked about yesterday, the energy of the inflation, because it keeps rolling down the hill, starts to slowly decrease as a function of time. So what that means is that at an earlier stage, you expect a bigger fluctuation. At a later stage, you expect slightly smaller fluctuation. So as a function of the time, as the universe is doing inflation, then size of fluctuation starts to decrease. And what you can do is to measure the size of fluctuation from the data as a function of the wave vector in the universe today, so that the k is the inverse length scale. So the larger k corresponds to smaller distances, smaller k corresponds to larger distances. So the larger scale corresponds to the earlier moments of the inflation, and the larger k corresponds to later moments of the inflation. And you can see that there is a slope. So the size of the fluctuation is not really constant. And when it's exactly constant, you say that's a scale invariant density fluctuation, but it changes slightly as a function of distance scales. And let me emphasize, this is really slightly, because here the scales change by 4 orders of magnitude. But over 4 orders of magnitude, the change in the density fluctuation amplitude is, as you can see from data, only from 3.25 and 3. So it's only a slight change. This is actually the exponent, so I have to be careful when I say this, but you can see this is really a slight change. And you parameterize this behavior in terms of the simple power law, and this NS is what describes what is called the spectral index. And the data suggests that NS is something of the order of 0.95. So 0.95 and -1 nearly cancels. So the K dependence is very slight because of that. So this is another strong support for the idea of inflation, because here everything is happening on logarithmic scales. So it really does suggest that something that goes exponentially is the right idea to understand this data. And so both the fact that the fluctuation seems beautifully Gaussian, and also that you have this power law, very simple power law, extending over many orders of magnitude. Both of them are believed to be very strong support of the idea of inflation. But if you want, go ahead.
Yeah, go ahead, Jeremiah.
Yeah, thanks. I have a question on, are you gonna talk about any possible deviation from this power law outside of the range that's been observed?
I wasn't planning to talk about it, but the people, of course, did fit to the data, allowing for deviation from the power law as well. So that is usually called the running spectral index. The NS here is written as a constant, but maybe NS can also change logarithmically as a function of K. And the people did the fit, and it's basically consistent with 0, but you can argue about it. And we don't have very good data when K is actually bigger than this number, because that's when the cosmic microwave background data runs out. You have to rely on other sorts of data like galaxy distributions, but then the error bars actually become pretty bigger. So we don't have that good information about what the power spectrum looks like at much smaller distances or larger K.
Right. I'll ask you later after you're done about possibilities.
Okay.
Thank you.
I have a question, Hitoshi. Is that okay?
Oh, go ahead.
So your explanation of this tilt is very nice, but now I'm confused because this picture seems to suggest that any flow or information you get a tilt like this. But if I remember correctly, hybrid inflation predicts opposite tilt, right? But that's you also have a rolling potential in that case. So how does it work in that case?
hybrid inflation is a little complicated because you have basically sort of completely flat surface at the point of this watershed, the potential. So the even calculation of fluctuation used to be controversial. And now there is a much better formulation to actually do so. And if you actually do it, they claim, at least I haven't worked on this myself, but the people who work on the claim that you can actually get something consistent with the data. So what used to be old calculation was in some sense not quite correct formalism for it because of the special feature of the potential having this flat surface. So it's not the fluctuation of the inflaton by itself, but there's the opposite direction that also fluctuates at the same time. And that's why it was more complicated. People had to develop a formulation for that.
Oh, I see. I should revisit my old work because I thought that was excluded because of the opposite tilt.
Well, as I said, I haven't worked on it myself, but that's the claim I learned from them.
Thank you.
Okay, so here's how inflation seems to be actually very well supported by the data, which is great. But of course, then we'd like to actually test it. And one of the tests is really this idea that when universe is undergoing this inflation, you are stretching the space in an incredible rate, and then space itself starts to wobble. And that wobbling, of course, is the gravitational wave. And if you want to be more mathematically accurate, then you can treat the metric field and decompose that into modes. Then each mode of the metric basically starts looking like an individual scalar field. And we have, of course, two modes of the gravitational field. And then each of them starts having this quantum fluctuation. So that's the way you have quantum fluctuation producing a metric field, which varies from one place to another. And once that is stretched over the horizon scale, then universe, quote unquote, observes the from quantum fluctuation and wave function collapses to a particular classical value of the metric field. And once it becomes classical, and that is basically the gravitational wave. So we hope to actually observe the gravitational wave coming from this inflationary era, and that becomes basically a very hot subject and in some sense holy grail of cosmology. But if you really would like to observe the gravitational wave coming from inflation on this huge distance scale, this is the inverse megaparsec. So this 10 to the minus 3 corresponds to gigaparsec, that's 3 billion light years. Then the wavelength of the gravitational wave you're talking about is also of the order of many hundreds of millions of light years or even billion light years. So what do you end up needing if you would like to actually send up a space probe like LISA is send the probes far away over billion light years. And you can't do that. You can't send out the laser wave back and forth over that billion light years because signal takes billion years to reach you. So that's certainly not practical. So that's why you have to come up with different ideas how you can see the impact of gravitational waves. And then that's the idea is to use the CMB polarization. So because the gravitational wave is basically wobbling space and time, the CMB photons get also wobbled by the gravitational wave coming from the inflation. And when the photons get wiggled, they can develop the polarization. And the mathematics tells you that there are two kinds of polarizations. One is called the E mode, which looks like sort of the gradient of Coulomb potential. Another one is called the B mode, which is like a curl or sort of like a magnetic field. And both polarizations can be produced from the impact of gravitational waves. However, E mode polarization is copiously produced in CMB photons because of just the Thomson scattering. Whenever you have the scattering of electron and photon, the photon will be polarized. And that's what you actually experience daily, especially in Florida. If you go to the beach and you have this incredible glare from the ocean and you get blinded. But if you put on the sunglasses with a polarized lens, then you can cut down on glare almost completely. And that's because the scattering of light from a flat surface like the ocean is extremely well polarized in the horizontal direction. So whenever you see the scattering of light, that produces polarization. And that's dominantly, that's always E mode. So E mode polarization is actually not great for the purpose of looking for the gravitational wave impact. And it's useful for other things, but it's not for looking for gravitational wave from inflation. That's why the focus has been on this B mode polarization. And so the idea then is that you have this gravitational wave coming from the inflation, and here's a CMB photon, and that develops this B mode polarization, and that's what you like to actually observe. And there have been many analyses of the data looking at this primordial tilt. Then the most preferred value is almost 0.96. And then this, the vertical axis is the fraction of the density fluctuation in gravitational wave relative to the overall density fluctuation. And that's a ratio called R. And right now, the data suggests that R has to be less than 0.05 or so from this fit to the data. And this I took from the paper from the Planck satellite collaboration. And what is also shown here is the predictions of various inflationary theories. So simple example I have shown in animation use the potential being just purely quadratic. And that quadratic potential makes the prediction up here. So it actually predicts relatively large component of the gravitational wave in perturbation. And that is already outside the region of preferred, the preferred region from the observational data. So not only that the data suggests the general idea of the inflation, data is getting precise enough that it starts to constrain what kind of inflation actually is supported by the data. And this is really mind-boggling. And the inflation back in 80s, of course, that was before I joined the community, but back in those days, it was supposed to be, in some sense, a little bit of a fringe idea. Well, it's kind of nice, but no, you will never know. It's such a remote thing, it seemed. But now it's really getting to the point that we can start discriminating one model inflation over the other. And so here we are. So we would like to learn more and try to eventually understand what exactly was the potential of the field that caused the inflation with much better data. So that's where we are. And one particular model that is plotted here is in some sense sort of prototypical model of inflation called the Stravinsky model. And I'm going to show you what that model is. So the Stravinsky's model is actually written by this Lagrangian, and I don't spend much time actually explaining it, but you can recast this Lagrangian into the form of the scalar potential that looks like this. And you can see that when phi is small, then this exponential when phi is large, this actually gets exponentially suppressed. Then you have a constant energy density. But as phi starts to roll down the potential towards the origin, at the origin, this is 0, exponential is 1, that cancels 1. So the minimum is really at the 0 energy density. So it has a nearly flat potential when phi is large, which is exponentially depressed, but eventually come close to the origin where you have basically a parabolic potential. And so that's the prototypical example of a potential people use for the purpose of inflation. And this is what I said in words on the previous slide. This is the formula I had actually earlier yesterday. And this is the amount of fluctuation you get from the quantum fluctuation for the metric tensor. And then what you see here also is that amount of fluctuation is simply given by the Hubble constant during the inflation. Hubble constant squared is given by the energy density of the inflation. So once you measure this amplitude of the tensor fluctuation, namely fluctuation in the tensor field of the metric field, and that tells you the energy scale of the inflation. So that's in one-to-one correspondence. So if we manage to measure impact of this gravitational wave, you have determined at what rate universe was expanding at the time of the inflation. And that's, of course, a very valuable piece of information. And there are many experiments being planned for this. The United States is pushing for this project called the CMB Stage 4. And the community is just finishing up Stage 2 experiment, heading to the Stage 3 experiments now. But Stage 4 is, of course, the future. And that's when you would like to mount various experiments. One of them is going to be on South Pole, where air is frigid and you don't have much water in the air. And that is a good thing if you would like to detect the radio wave for the CMB. And another place, a famous place, the Atacama Desert in Chile, and that is at the altitude of something like more than 5,000 meters. And because of the thin air, again, you can avoid impact of the atmospheric issues in looking for the radio waves. So these are the sort of prime sites people are talking about for mounting these experiments. And it's going to actually be a tremendous scaling of the kind of experiments people are doing these days, which has something like 1,000 detectors, like a transition edge sensors to detect the CMB photons, going to stage 3, that's 10,000, and stage 4, 100,000 of detectors mounted in a big array, and to have more pixels and better accuracy so that you can have a sensitivity going down to the level of 10 to the minus 4 microkelvin. In the fluctuation in the CMB temperatures. And of course, you put the polarizer in front of it to make sure that you actually measure the intensity as a function of polarization. And that's how people would like to actually make progress in looking for the impact of gravitational waves by looking for the B-mode polarization of the CMB photons. But there's also a project that is being planned in space, which is called LightBird. And the problem of actually doing this kind of experiment is the foreground. We happen to be living in a galaxy, and galaxy is bright, not only in optical light, but also in radio. And much of the radio wave is also polarized. So that gives you the foreground, namely that it's a noise you would like to avoid. And of course, the thinking about this kind of the polarized radio coming galaxy has its own scientific interest. That's the way you can study the magnetic field. That's the way you can study the dust in galaxies. So the people would like to study that too. But again, for the purpose of looking for the polarization in CMB photon, that's a foreground, that's a noise you would like to avoid. And compared to the level of the noise on this plot, you see what you're expecting for the signal is actually buried in the noise. So you have to do a very sophisticated analysis to dig out the signal you're looking for, basically fitting this foreground noise, having measurements at many, many bands of the frequencies. So in order to actually do this experiment, our friends are working on this LightBird satellite, decided to have this many frequency bands so that you can reliably fit the noise spectrum coming from the synchron radiation due to galactic magnetic field and the emission of the light from the dust in the galaxies. And by having this many bands of the frequencies, they believe that they can reliably subtract this noise to dig out the signal we are looking for. And there are many kinds of reasons why you do want to go to space, because again, the atmospheric disturbances. And you see the spectrum of the radio wave from the atmosphere on the Chilean site. And so this is actually something you would like to avoid, again, compared to the signal of the CMB down here. So you don't have access to the entire range of the frequencies if you're actually doing CMB observation on the ground. And these things are, of course, gone once you go to space. But of course, going to space has a definite disadvantages. It's expensive to begin with. And you have to make sure that the instrument is completely robust, because you can't go out and fix things. And so that means you have to actually plan ahead and use relatively sort of older version of technology to make sure that there's nothing go wrong by just going to too much of a high tech. And so that's much more difficult technological endeavor. But nonetheless, having both ground-based observation and the space observation would be useful. So in order to be able to probe this prototypical model of the Stravinsky model, you are looking for this R ratio of the gravitational wave fluctuations over the overall density fluctuations. And this ratio R is predicted in this model to be actually less than 1% of the order of 3 per mil. So what you want to design is an experiment that has sensitivity going down to the level of R being per mil, 10 to minus 3. And once you have this kind of sensitivity, you have something like a 3 to 5 sigma signal of the Stravinsky model in the gravitational wave impacting the B mode fluctuation. And that's what people are after. So both the ground-based experiments, CMB stage 4, and this space-based experiment, the LIGHTBIRD, are aiming at this threshold of the 10 to minus 3 in the tensor to scalar ratio R. And so this is the way the spectrum looks like. So there have been actually observation of the B mode polarization in CMB photons already. But that's actually didn't make the news because that's actually not the signal of the inflation. Then what's causing this B mode polarization at very high L, which corresponds to smaller angular scales, if you remember, is the fact that CMB photons are emitted at the 13.8 billion light years away, and they are coming towards us, passing through everything in between. And so in particular, there are many clusters of galaxies in the intervening path of the CMB photons. And the gravity from the cluster of galaxies would bend light. And that's what is the effect called the gravitational lensing, because the mass, like the cluster of galaxies, behave like a magnifying glass. So they bend light. And that bending of light also induces a B mode polarization in CMB photons. So what has been detected here is believed to be the impact of this gravitational lensing effect, and that's consistent with the theoretical expectation in this solid line. So this is already a proof of principle that you can detect B mode polarizations in CMB, which is fantastic. That have been done in experiments both at South Pole in Chile. And so you can detect B mode polarizations with the current technology. So that's the good news. But in order to really see the impact of this primordial B mode polarization, namely the impact of the gravitational wave coming from inflation itself, you need to look into the smaller L. And the ground-based experiments I mentioned earlier are planned to get down to the level of L of 50 or so. And the reason why you can't go to smaller L on the ground is because your detector is sitting on the ground. Earth rotates, but it has a coverage of sky, not entire 4 pi, but only a limited portion of it, simply because you're sitting on a particular location. So the ground-based experiment does not have access to the full 4 pi of the sky, and that's why you cannot access very low L. And going down to 50 is already very ambitious. On the other hand, when you go to space, then your satellite can go rotate into arbitrary directions, so you can cover the entire sky. But of course, you can't put a very heavy instrument on a satellite. So that's a compromise. You have a good sensitivity on low L, but the space-based experiments can go to a very small, large L. So that's the complementarity. The ground-based experiments can go from L over like a 50 to a few thousand. Space-based experiment like LIGHTBIRD can go from very low L to something like a 200. But it's great that they overlap in the middle, so they can do a cross-calibration between totally two different measurements. And that's how they believe that they can actually achieve the kind of confidence in measuring lensing B mode spectrum all the way as a function of L, from small L to very large L. And this is the current data set. But in the future, with experiments like LIGHTBIRD, that they're expecting this small error bars. And the difference of this data points, this is of course a simulation data, in showing in this dashed line in black beneath these data points, and this thick solid line, which is what is expected from the gravitational lensing effect. So that's not the signal you're looking for. So what you're looking for is a difference between this dashed line and solid line. And that's a tiny signal, as you can see. But that's something they believe they can dig out. So this particular plot is shown when R is 0.01, 1%. When R is 10 to the minus 3, that's the limit of sensitivity, you get the signal that's 10 times smaller. But you can sort of see by your eyes that that's sort of the limit you can have sensitivity to. And so that's the way that these experiments are designed. So by combining ground-based observations and space-based observation, you want to map out the spectrum of the B mode fluctuation power spectrum as a function of L. And the inflation predicts this characteristic shape of this the power spectrum. And so once you see this particular shape, and in a consistency between space and ground, And then you can believe your data set, and then you can finally claim that you have observed the impact of gravitational waves coming from inflation. So that's the holy grail of the modern cosmology. So we would like to see that you can actually get back to the stage of the inflation by looking for the gravitational wave emitted from the inflationary universe itself, and that the gravitational wave would affect the beam polarization of the CMB photons, and you are going to measure the power spectrum of the beam polarization of the CMB photons, and we hope that you can dig out this very subtle, small signal of the beam polarization, which turns out to be the evidence of inflation. And once you measure this evidence, as I said already, you have actually measured how quickly the universe was expanding while it was undergoing inflation. So that's the idea. And my lecture on inflation stuff is actually here is the end. And I'd like to move into other potential sources of the gravitational wave from early universe, from phase transition, and also cosmic strings for the rest of the lecture today. So let me stop here to see if there are any questions.
So the black line, so that will be your background. There is no error bar on that line. I mean, are we not going to know the background that precise to be able to dig out the B mode from the gravitational waves?
So this error bar is believed to be rather small because this is the consequence of gravitational lensing, which comes from the existing structure of the universe today, which you do observe using telescopes. So you can actually use the data to work out what the level of the gravitational lensing you expect.
Okay.
Can you take a question from a layman? I guess I would like to know if the speed of light or the speed of the gravitational wave transmission is constant in the sense of what it might have been under different conditions of quantum fluctuation and or different rates of expansion, inflationary expansion. Are we stuck with C equal to what it is under all circumstances in the past and the current state of the universe?
First of all, this whole discussion I had today assumes the general relativity, which says the speed of light is always a same number. So that possibility is not included in the discussion. And so if you want to actually change that, then you have to really change from general relativity in some way. And one of the important impact we had from gravitational wave, you probably heard about this, is this event of neutron star mergers, where people could also see the follow-up of the event after the gravitational wave by all the bands of the electromagnetic spectrum. So which was a good evidence that the gravitational wave traveled with the same speed as the rest of the electromagnetic spectrum. So at least we don't see any sign that there's any change in speed of light so far. But of course, if you would like to study that possibility, then you have to write a theory for it first. And that kind of theory had been studied by putting in extra scalar fields, which also slowly changes over a function of time, and so that the fundamental constants change according to the change of the scalar field. And that kind of theory people did look into. And I actually don't know myself how that would affect this signal of the B mode fluctuation in the presence of such an extra scalar field. So I don't know the answer to the question, but there are actually papers in the literature that looked into it. So I hope you can find those.
Thank you.
Sorry, that's the best answer I can give.
Thank you.
Oh, Vaja?
Thank you. I have one question. Is it possible in nearly future that we will be able to detect the gravitational waves from inflation directly without looking at CMB, or it is very weak for this purpose?
Yeah, so there is a possibility if the gravitational wave from inflation had been produced even at much, much smaller scales, so that the wavelength is actually not as large as this, but something within the sort of the distance scale where you can hope to do experiments. And that kind of idea does exist. So there are the concepts for missions called the Big Bang Observer in Europe and DISIGO in Japan, which actually do something similar to LISA, but specifically target the frequency range where you don't expect to see much of the astrophysical signals, which Champei must have talked about from black hole mergers and so on. So you look for the sweet spot where you don't have signal from astrophysics, so that you can dig out the signal from the gravitational wave from inflation. So that ideas do exist. And unfortunately, if you actually take the amplitude of the density fluctuation we observe in CMB, which looks nearly scale invariant, but becomes smaller at the short distances. And if you just extrapolate this down to the kind of short distances where you can imagine doing experiments, then amplitude looks too small. Having said that though, the inflation theory may not be as simple as a single scalar field. Then you may have, for example, this slope going down and down to smaller scales, but at the very small scales, you might have a bump. Then you have a chance. So whether that is actually a sensible thing to do depends on what kind of faith you have in the simple inflationary model. And if you have a little bit more complicated model, you still do have a chance of observing gravitational waves directly from inflation. So that's where the situation is.
Thank you very much.
Okay, Pablo?
Thank you, Toby. I really like the plots that you had where you showed the structure that was formed comparing if you had dark matter or those plots. That was amazing. Thank you so much. So my question is, if I understood you correctly, if you don't have dark matter, that means gravity will not be strong enough to convince those small fluctuations to actually enhance and create the galaxies and all the overall structure that you see.
Right.
How do you rule out something like you have a changing G constant of gravity and maybe it was stronger back then and then it got weaker?
Again, I'm not an expert on that kind of modified gravity theories, collectively called, but the fact that, excuse me, you can have this incredibly good fit of the CMB power spectrum using the current cosmological model, that this is actually a fit to the data using the theoretical model, suggests that the laws of physics we are using to do this fit, namely general relativity, seems to be correct. And of course, this is not a proof of GR. And if you want to prove this, we really have to work on the theories of modified gravity. That's what I was mentioning to the previous question, and then do a fit using that theory and start constraining the parameters. And so that's what you have to do. And unfortunately, I'm not an expert in that field, so I don't know really the answer to that. But this seems to be already a very good, convincing circumstantial evidence that the changing G is not really what's going on, at least in my mind.
Okay, that makes sense. Thank you.
Okay, Jeremiah?
Yeah, if you don't mind, go back to that plot, which is showing the running of this power spectrum. Yeah, that one. So you actually just described the situation that I was curious about, that as you go to smaller scales, what are the possibilities that the power spectrum goes up again? And you just gave another example of why one might be curious about that. The other one that I'm curious about is people are taking primordial black holes seriously as a form of dark matter. However, I have heard, I haven't done the calculation myself, I have heard that in order to get those things, you would need this power spectrum to jump up by many orders of magnitude at the small scales or large Ks here. And so my question for you is how could you possibly get the power spectrum to jump up by many orders of magnitude? What are the ideas out there? Yeah,
so you basically have to come up with the models of inflation that does this jump. So you have, just to put in an idea, let's say you have two different scalar fields. And the first scalar field happens at the earlier stage of the inflation, and second field happens at the later stage of the inflation. And they have very different shapes of the potential, so that they give you different magnitude of the density fluctuation for these two parts of the inflation. So basically having two inflations and giving you different spectra at small scales and large scales. And that's the kind of thing people indeed do for the purpose of creating primordial black holes to explain the dark matter, or even explain the LIGO data for the sake of the argument. So that's what people have tried. And once you have this kind of spectrum, again, you might have a chance of detecting gravitationals directly from inflation at small scale experiments. Small in this case means solar scale, so it's not ground-based, but anyway, so that's what some people are talking about.
I'm curious, what's the frequency range that people are considering for these things?
In the case of primordial black holes, you're talking about the horizon size at the time of the QCD phase transition. So scale today would be, let me see, that will be sort of the LISA kind of wavelength.
Okay. Okay, thanks.
Just a brief follow-up. Would primordial black holes potentially affect spectral distortions later or non-Gaussianities if you got down to that sensitivity level?
Yes. In fact, the primordial black hole is believed to be produced in a very tail of this kind of the fluctuation. So, so what you need is that only very small parts of the universe just happen to have large enough size of the fluctuation so that they collapse into the black hole. So in order to actually do this efficiently, people come up with a non-Gaussian distribution fluctuation so that it has a longer tail in a higher amplitude, for instance, to allow for the possibility of the forming black holes are efficient enough for the purpose you like. So people come up with all kinds of more complicated inflation models to design both amplitude of fluctuation and also distribution in fluctuation. So you're completely right about that.
Yeah, thank you.
Okay, so the last question is by Susan.
All right, there we go. Thank you. So I'm wondering if there's any correlation between the distribution of the galaxies seen by the Sloan Digital Sky Survey and the temperature fluctuations in the CMB.
There are correlations, but not in the way that they are looking at the same fluctuation directly, because the CMB photon is telling us the fluctuation, which is really at this last scattering surface of 13.8 billion years away. And Sloan's Digital Sky Survey is looking at the fluctuation that are happening on sort of 100 million light years to a billion light years away. So you're looking at different positions in space, basically. So they are independent from each other. But you can test whether the spectrum fluctuation is consistent with each other. And that's what people indeed do. So from the data like Sloan's Digital Sky Survey, you compute the power spectrum in galaxy distributions. And whether you can test whether the size of the power spectrum galaxy distribution is consistent with the normalization you would expect from the size you see in a CMB power spectrum. And they are basically consistent with each other. So you're not looking at the same fluctuation, but you are testing the consistency of the source of the fluctuation coming from inflation that way.
Okay, thank you.
Okay, I think you can go to the phase transition.
Okay, so the rest of the discussion, I think I have to keep rather brief because I'm already have something like only 30 minutes left. And so now that we have this idea that gravitational wave can be a useful tool for us to peer through this thick cloud of the early primordial plasma, looking at the incidents at the early universe events. And one of the such events that might cause a gravitational wave is the phase transitions. So the idea again is that CMB photon can only probe back to this last scattering surface, 300,000 years old universe. And using gravitational wave, we want to actually look further back into the early universe. And one of the things that can happen is some kind of phase transition. So you need to set up some rather complicated potential for this purpose, but the idea is this. Suppose you have some kind of potential or free energy of a certain order parameter, and so that you have a minimum at the origin at high temperature. But potential has a particular shape that as the temperature comes down, at some point, it develops the second minimum. And once you have the second minimum, what you used to be here, but then you can tunnel quantum mechanically from this minimum to that minimum, which ends up being the absolute minimum at the lower temperature. So that's when you expect a phase transition where order parameter changes, discontinuously, from this value here, and when you tunnel, you all of a sudden has this value instead. And this continuity in the physical quantity is the first order phase transition. So that's the way you describe, for example, the condensation of the liquid water droplets from the vapor as a first order phase transition. If you would like to describe this in terms of free energy or field theory, then this is Landau theory of the phase transitions, as as it's known. So once you have this kind of phase transition, then interesting things happen. Basically, that when you are boiling water, then you hear the sound of boiling water because you create the bubbles of the gas phase within the liquid, and those gas phase form a bubble. The bubbles coalesce, that actually percolate, that actually collide with each other, and then you hear the sound of it. The fact that you hear the sound of it is that this dynamics of bubbles is shaking the system. It not only that shakes the liquid, it can shake also space-time, and then that's the source of the gravitational wave. So if you have what is called a strongly first order phase transition, you have a possibility that can also lead to the emission of gravitational waves. So when you have this first order phase transition, then you have two minima with the same energies for a while. So that starts to form these bubbles, just like in the case of the water, I use that as an analogy. And the bubbles of this lower temperature phase start to grow. They actually fuse together and eventually cover up the entire space to complete the phase transition. So you have these bubbles forming, colliding, merging, and eventually completing a phase transition. And that is the process people simulate and then study how much gravitational wave can be emitted. This is just sort of an artistic conception of how the phase transition may be happening. And that's one can also hope for in seeing the impact on gravitational waves. And because these the phase transitions happen at the characteristic the temperature scale, the spectrum of the gravitational wave you would predict from the first order phase transition happens to have this kind of peak. And the location of peak basically corresponds to the temperature of the critical temperature of the phase transition. And that's something you can hope to see in the gravitational wave spectrum. So what's plotted here is just some generic version of first order phase transition, and never mind what model they use for this purpose, because this is fairly generic. And it plotted it as a function of different critical temperatures of the phase transitions. And here, green corresponds to 5 TeV. Here's 2000 TeV. And that's the energy scale no accelerated experiments have probed yet. So you have this possibility that there may be some kind of phase transition happening at those temperatures. And depending on what critical temperature is, you have the different peak wave frequencies. And compared to that, you see the coverage of the ground-based gravitational wave observatory and space-based gravitational observatory. So depending on what the temperature is, you might be able to actually see the impact of that kind of phase transition. By the way, in responding to the question of primordial black holes, that also has the characteristic distance scale, which corresponds to horizon size. And to get the kind of size of the primordial black holes needed for the purpose of getting dark matter or the LIGO events, I said this is in a LISA range. And you can sort of see that this temperature changes would bring it into the LISA range when temperature is lower. And when the temperature is about the 100 million electron volt, that's 4 orders of magnitude smaller than this. So that peak would shift basically by 4 orders of magnitude this way. That gives you about the primordial black holes of the solar mass scale. So that's why I said that it is sort of basically in the LISA range for that purpose. That comes with the basically same scaling law, where the peak of the gravitational wave spectrum is corresponding to the size of the horizon and the temperature when things happen. So this is something you may detect from the phase transitions in the early universe. But at this stage, I'm just talking about sort of generic first order phase transition. I'm not giving you any reason why you would expect to see this kind of phase transition in the early universe. And I have to actually sort of skip over that discussion. But that actually leads us to the discussion of the origin of the baryon asymmetry of the universe. So you have seen this pie chart many times, and we always talk about these mysteries on what dark energy is and what dark matter is. But if you think that you understand this 5% of the universe made up of atoms, you're actually an optimist, because we actually don't know these things exist at all in the universe. So when universe started out with inflation, that's the idea we talked about. And energy of the inflation then turns into the thermal energy of the thermal bath of the early Big Bang. And when energy turns into the mass, namely by equal mc squared, we all know that energy turns into the pair of matter and antimatter. So photon can turn into a pair of electron and positron, proton and antiproton, but it's always 1-to-1. But if it stayed that way, then universe would have been filled by the same amount of matter and antimatter. And as the universe cooled, then matter and antimatter would eventually meet. They would annihilate 1-to-1, and they all disappear. So if the beginning of the universe right after inflation has the same number of matter and antimatter, then they would all meet and completely disappear, and universe would have been empty. And you wouldn't be here to listen to my talk today. So clearly, this is not what happened. So something else must have happened. And what we know from the data, again, using cosmic microwave background, is to infer the amount of the baryons we have in the universe today. And you can compute this ratio called the baryon to photon ratio. So you have determined the amount of atoms we have in the universe based on CMB, this odd even peak ratio. You know the number of the CMB photons, and you can take the ratio, and that ratio turns out to be slightly less than 1 part in a billion. There's another way of determining the same number based on this idea called the Big Bang nucleosynthesis. So that's the idea that when the universe was from about 1 second old to about 3 minutes old, when the universe was only 1 second old, the universe was so hot that there were no atomic nuclei. Protons and neutrons were moving freely from each other because the binding energy of the nucleus was too small compared to the energy of the thermal bath. But as the temperature cooled, the protons and neutrons start to meet with each other and start forming the bound states into, for example, deuterium, and eventually go into helium-4 or lithium-7. And that is the process that should have happened in the entire universe, called the Big Bang nucleosynthesis. And by measuring the amount of deuteron we have in the universe today, which you can predict as a function of the baryon to photon ratio, then you can fit the data, which is actually shown in this band here, compared to the theoretical expectation and infer what the baryon to photon ratio is from the amount of deuterium you observe in the universe today. And that turns out to be very much consistent with what you infer from cosmic microwave background data. And this is actually believed to be a tremendous success of modern cosmology, because you're comparing data between what should have happened when the universe was 3 minutes old versus what happened when the universe was 380,000 years old, and you see a consistency between them. So this actually makes us believe that we know this number very well, namely baryon to photon ratio, which is less than a 1 part in a billion. And the fact that you can actually measure the amount of deuterium in the universe today is actually sort of a curiously simple observation here, that when you look at the absorption lines from Lyman spectrum in hydrogen atom, the energy levels are written as a function of the reduced mass. And when you look at the hydrogen atom of the ordinary hydrogen with a proton as a nucleus versus you look at the hydrogen atom with the nucleus is actually deuterium instead of the just pure proton, their masses are of course doubly different. And the proton mass is about 2,000 times heavier than the electron. So the change in the reduced mass in the energy levels is different at the level of 1 part in 4,000. But that's something you can do spectroscopy to determine the difference in the energy levels at the level of 1 part in 4,000. And what you're seeing here is absorption line from the hydrogen and absorption line from the deuterium can be separated from each other. And that's how you can determine amount of the deuterium you have in the hydrogen gas. So that's how you know this deuterium to hydrogen ratio, and you can compute deuterium to hydrogen ratio as a function of baryon to photon ratio theoretically, and you look at the point where they cross, and that's how you determine this baryon to photon ratio, which happens to be very much consistent with what you inferred from cosmic microwave background. So that's how we think we know this consistency of understanding this baryon to photon ratio. So what must have happened then is the following. So starting from the same number of the antimatter and matter produced by when the inflationary energy converted into the form of the matter, but something changed, namely that you change 1 out of a billion antimatter into matter somehow, so that now you have an imbalance between the amount of matter and antimatter. And when they, of course, eventually meet, much of that disappear, but basically 1 part in a billion remains, and that's you. So this is the only way we can understand how we could survive the Big Bang. So we survived at the expense of a billion friends. So you should be really, really grateful to them. They did an ultimate sacrifice for you, and we survive. But as you can see, the main player here is this process, which reshuffled the amount of matter and antimatter somehow. You changed 1 antimatter out of a billion or so into matter. And we have never seen a process experimentally that matter can turn into antimatter or vice versa, but clearly there's a need for that. Otherwise, you wouldn't be here today. So this is the idea called baryogenesis. Somehow you reshuffle the amount of antimatter and matter. You pick 1 antimatter out of a billion and manage to turn into matter for some reason. And we need to have that kind of process to understand why we exist in the universe today. And we could have argued that maybe that was the initial condition of the universe. But we can't do this anymore now that we believe in inflation to a great extent, because inflation stretches out the universe by such an extent, whatever initial condition you might have had will be totally wiped out. So that's a big reset button as far as this asymmetry between matter and antimatter is concerned. So you have to start anew after the inflation. So you need some microphysical evolution process of starting with a 0 asymmetry to a small but finite asymmetry as a consequence of evolution. And we are evolving in a different state of matter today, it seems. But anyway, so that's something we need. So we believe inflation, we already talked about it, and we need to have this process of changing 1 part of a matter, antimatter, into matter so that we will survive, we could survive the Big Bang. So, somebody saved us from a complete annihilation. So there must have been a superhero for this. And in order to actually explain this puzzle, called the baryon asymmetry of the universe, there is the famous conditions put forward by a Russian physicist, Sakharov, who was actually a big dissent in the communist government in Soviet Union, and he had been jailed many times. But eventually, he was actually freed. And in the middle of this political fight, he was, of course, great physicist as well. And he came up with these 3 necessary conditions for us to understand how universe might have created this imbalance between matter and antimatter called the baryon asymmetry. So clearly, we need a process where the baryon number changes. Namely, you need to change matter into antimatter or antimatter to matter somehow. So that is a process we have never seen experimentally so far, and that is a process called the baryon number violation. Even if you do have a process that can shuffle matter and antimatter, you need to prefer matter at the end of the day, not the antimatter. So you need to have some difference, fundamental difference in the behavior of matter versus antimatter, so that you have a distinction for the universe to choose one over the other. So this behavior, the difference in the behavior between matter and antimatter is called CP violation in the particle physics jargon. But the idea, I hope, is simple. You need to have some distinction built in in the behavior of matter and antimatter, so that using this process that can change matter into antimatter, somehow we would prefer to go into the direction of the matter by the universe in its evolution. So you need the second ingredient called CP violation. But that's not enough, it turns out, because if the universe always stayed in thermal equilibrium, which is the way we often think about the Big Bang universe, equilibrium, by definition, has a detailed balance between whatever process you have in one direction to the inverse process. So when you have the detailed balance between the process and inverse process, the system is in equilibrium. But if that's the case, even if you have this barrier number violation, so that you can change matter to antimatter, and even if you have CP violation that has a certain direction of the arrow in preferring the direction of the matter, if you have the detailed balance with the inverse process, again, you don't gain anything. So that's why you need to also have a period where the universe actually has a departure from equilibrium. So these are the three conditions put forward by Sakharov if you want to understand the origin of the asymmetry between matter and antimatter at the level of 1 part in a billion, so that we could survive the Big Bang. But it's a single number. People came up with all sorts of theories trying to explain this. And so we have to actually focus a little bit on what kind of theory we want to look at when you discuss the potential signal in a gravitational wave. And one such sort of a well-motivated theory that explains the difference between matter and antimatter is the idea that the neutrinos are the superheroes. So here is a nu in the logo over here. And the reason why neutrinos can be actually important for this purpose is that it is the only matter particle that does not have an electric charge. So in principle, neutrino, which is a matter particle, has a zero electric charge, can turn into antineutrino, which has electric charge -0, which is the same thing as 0. So neutrino is the only candidate elementary matter particle that can, in principle, go back and forth between matter and antimatter. So that's the one very attractive idea. And that actually doesn't work if the neutrino were massless. But it turns out that the mass of the neutrino had been discovered in 1998, and Kajita received the Nobel Prize for this in a process called the neutrino oscillation. And after this discovery, I also got involved in a neutrino experiment called CAMLAND, where we detected the neutrinos coming from nuclear power plants, which were actually quite dominant in Japan in those days. And after Fukushima incident, they all went quiet, and they are not producing neutrinos anymore. So we had an opportune moment to study neutrinos before the Fukushima incident. And by using a tank of basically mineral oil called the liquid scintillator, we could detect the anti-neutrinos coming from nuclear power plants. And we could really observe this behavior of oscillation. So neutrinos produced from the source, you know the amount of neutrinos produced at the source, they seem to disappear, reappear, disappear again, reappear again. So in the data, we could actually observe 2 cycles of the neutrino oscillation using these neutrinos coming from nuclear power plants. And what that means is that the neutrinos oscillate, namely that they sense time. And when something is going with speed of light, then the time dilation effect would stop the clock. The fact that neutrinos seem to change on their own, namely they sense time, must mean that they are going at a speed less than speed of light. But if something is traveling at a speed less than speed of light, it should have a finite mass, because anything that doesn't have a mass, including the photon and gravitational wave, should travel with speed of light, but neutrinos apparently don't, therefore they must have a finite mass. And that is actually the key for this idea. So they have mass, it's finite, very, very tiny compared to other masses of elementary particles, but nonetheless, they have a finite mass. And I see a chat over here. Okay, good. So that's where people came up with this idea called the seesaw mechanism. So we really would like to understand why neutrino masses are so small compared to all the other masses. If the mass was 0, there was nothing to be explained. But now that the mass is finite, but so tiny, at least 1,000,000 times smaller compared to the smallest other particle masses, which is of the electron, we would like to understand why so small the neutrino masses. And the reason why this is kind of important is the following. We know experimentally that all neutrinos are left-handed, namely that when neutrinos travel space, they have spin 1/2, but they always spin in counterclockwise fashion, which is called the left-handed neutrino. So neutrinos are all left-handed, they spin counterclockwise. But now that they have mass, so they are not going speed of light, and young students in the audience can probably run faster than it, then so you can actually take it over, and from your rest frame, the neutrino is actually moving backwards. But that doesn't change the spinning, so you would observe a neutral fermion, which now spins clockwise. But we have never seen a right-handed neutrino experimentally. But we have seen right-handed neutral fermion, which is actually an anti-neutrino. So if you actually overtake neutrino and observe neutrino being spinning clockwise, you may be actually looking at the anti-neutrino instead. So that's how the neutrino and anti-neutrino can turn into each other. And in order to achieve this possibility theoretically, and what you have to do is to introduce a genuinely new heavy particle, which I call N in here. And this N particle is very heavy, so that the mass of the neutrino has this now matrix of this N particle and the neutrino we observed. And when you diagonalize this matrix, then you find the mass eigenvalue to be extremely suppressed by this heavy mass. And this is the way you may understand why neutrino mass is light. But you have given up something, namely that you have given up fundamental distinction between matter and antimatter. But that's exactly what you want for the purpose of reshuffling the matter into antimatter and vice versa in the early universe, so that you can have an imbalance between them and so that we can survive. So that's the idea of the seesaw mechanism. So you introduce this very heavy neutral fermion, which is called a Majorana fermion. And that's one of the holy grails in condensed matter physics these days, looking for an excitation in topological insulator where you see a fermionic degree of freedom with no charge. And that state can be antiparticle of its own. And then you say that fermion is a Majorana fermion. So neutrino could also be a Majorana fermion, so that the particle and antiparticle are actually the same thing, depending on how you look at it. So when you look back at the neutrino, then you see an anti-neutrino. So now that the mass neutrino has a mass, this possibility of the Majorana neutrino all of a sudden became very plausible. Hence this idea called the leptogenesis. So this N particle I talked about is very heavy, but heavy particle can be produced when the universe had a very high temperature. Temperature is bigger than mc squared would allow these particles to be produced from thermal energies. And so this N particle is a Majorana fermion, so it's an antiparticle of its own. So it can decay into ordinary neutrinos, but also into antineutrinos simultaneously. And at the level of the lowest order perturbation theory, you would predict that this particle, which is the antiparticle of its own, would decay into ordinary neutrinos and antineutrinos with a 50-50 probability. Then you don't gain anything in terms of the imbalance between matter and antimatter. But it turns out that if you go to a high order perturbation theory, you have another process which can pick up CP violation, which is reflected in the complex coupling constant. And CP violation would produce different probabilities of this N particle decaying into ordinary neutrinos or ordinary antineutrinos at the level suppressed by the higher order perturbation theory, but which may still be sizable. So when you produce a bunch of these particles in the early universe, all you have to do is just let them decay. And when they decay into neutrinos and antineutrinos, but now with different probabilities. So then you end up having small difference between the amount of neutrinos and antineutrinos in the universe. That's the origin of the asymmetry between matter and antimatter. And that became basically a dominant paradigm in neutrino physics community. And so this is actually a tiny neutrino mass that is giving us this possibility that matter and antimatter can turn into each other, which in turn gives you this new degree of freedom, which happens at a very high energy scale and high temperature towards the beginning of the universe. And so that actually makes it, of course, notoriously difficult to test as well, whether this kind of particle really did exist in early universe. But idea is that once you have this heavy neutrino, a Majorana fermion, they mostly decay with the same probability into matter and antimatter, but the probability may be different at the high order perturbation theory by small amount. But small amount is okay because what we need is the difference at the level 1 part in billion. So this became a very attractive idea now that we did discover the finite mass of the neutrino. And so that's why we actually want to see if this is a real possibility. Now, how am I doing with time? So how much time do I have left? 10 minutes left. Okay, I think I can finish this story. So it turns out that if you actually do a more serious study on what kind of the mass of the neutrino you need for this purpose versus what kind of mass you need for the heavy N particle for this purpose, the kind of mass we talk about for the light neutrino masses turns out to be the right range. On the other hand, this heavy N particle you need is really heavy, ranging from like 10 to the 10th GeV to the 10 to the 15 GeV. So it's very difficult to think about how you actually test the presence of this particle. For example, if you want to build a high energy accelerator to produce this kind of particle, then you need to build a very, very high energy collider, and with the current state of technology, and then you need to have a ring of the collider as large as a galaxy. So that would probably require not only international collaboration, but interplanetary collaboration too. So that's not what we're going to see in a lifetime. So you need to look for some circumstantial evidence, and this is what I call archaeology. So in archaeology, you don't recreate the history. But if you dig up enough of the fossils, which line up to give you a consistent story, then you think you understood what happened in history without recreating it. So we look for circumstantial evidences for the presence of this N particle in the early universe. And people are looking for a process called neutronless double beta decay. And this is a process where you're looking for certain nuclear decays where nuclear beta decay produces an antineutrino. But if the antineutrino can turn into a neutrino, neutrino can be absorbed by a proton with a second beta decay so that you produce 2 beta electrons, but no neutrinos. So that if you actually see that kind of process, that's an experimental evidence that the antineutrino can turn into neutrino, and that will be a good circumstantial evidence that they can really reshuffle matter and antimatter. We know that kind of process can happen only once in 10 to the 26 years, which is way beyond the age of the universe. But if you collect specific nucleus like Xenon 136, 10 to the 27 of them, then you may be able to observe 10 such decays per year. So that's what people are trying to do experimentally. We haven't seen it yet, but that will be the evidence of the Majorana nature of the neutrinos. Another thing people are looking for is whether you have CP violation in the behavior of the neutrinos by looking for this oscillatory behavior and compare the behavior of the neutrinos oscillation and also behavior in anti-neutrino oscillation. If there's a difference between the two, and that's a sign of the CP violation, that's a second ingredient in the Sakharov condition. But as you can see, we are still looking for the evidence of the third condition of the Sakharov, namely departure from equilibrium. And right now, we don't have a way of looking for it. There are some other signals people talked about. This is very model dependent, so let me ignore this for the moment. So the question is, could there be more circumstantial evidences of this idea that neutrinos were the superheroes who saved us from complete annihilation? In particular, the presence of departure from equilibrium. And so the idea, let me skip some of the slides to save time, is this. When you have some kind of phase transition in early universe, which was very similar to the phase transition of the type 2 superconductor you can study in the laboratory. Type 2 superconductor can allow for this non-equilibrium situation that the magnetic field can be trapped in a tube of the magnetic field called Abrikosov flux. And this is a fairly common phase transition from the point of the field theory. If you have any gauge theory based on something called U1 gauge group, which is similar to electromagnetism in the case of superconductivity, then that kind of phase transition can produce also a flux of the magnetic field after the phase transition. And that kind of flux of the magnetic field produced in the universe is called cosmic strings. So in non-equilibrium situation of the phase transition, that would lead to the mass of this heavy N particle I mentioned earlier. And at the same time, that phase transition can also produce cosmic strings, namely that you have this trapped magnetic field everywhere in the universe in the form of these narrow tubes. That's why they are called strings. And energy of each string is proportional to its length. So once you start this complicated network of strings at the beginning, they start to stretch and simplify themselves to give energy and to settle down to lower energy state. And the way that strings will simplify themselves is by reconnecting, and so that you have a loop that will shrink and disappear, or that produces this kind of kink. And when you have this collision of strings or reconnection and forming loops or kinks, that would actually simplify the network like this. But as it starts to simplify it, you see more strings coming from outside the horizon into the visible portion of the universe. And so as it keeps simplifying, then you have more strings coming in. So for a long period of time, universe would have this nearly scale invariant behavior, namely that you keep having this network of strings, keep simplifying it in a sort of self-similar fashion, like what you see in condensed matter physics of the second order phase transition, like in the Ising model. So this self-similarity of this simplification process can lead to the spectrum of gravitational wave, which is also nearly scale invariant. So that's something you would predict theoretically as a function of the critical temperature of the phase transition. And this is the kind of the future observatories that are looking for gravitational waves in this kind of the frequency ranges. And what you see here is that by looking for sort of the far future experiment, in principle, you can cover this entire range of the critical temperature I mentioned for the purpose of creating a asymmetry of the matter and antimatter in the universe for us to survive. So this would be the test of the third circumstantial evidence that we might have this departure from equilibrium, which led to the Sakharov's condition to print the difference between matter and antimatter in the early universe so that we could survive the Big Bang. So this is yet another way the gravitational wave might be useful for us to peer through this thick primordial soup into the early universe. And in this case, we are not looking at the inflation, but rather the origin of the asymmetry between matter and antimatter imprinted in this network of cosmic strings. So that's another example I wanted to mention, where you can use the gravitational wave to look back at the beginning of the universe, very early stages of the universe, when the temperature was so high right after the inflation, but nonetheless, you might be able to actually get some information about it using the gravitational wave. Okay, so that's pretty much all I wanted to say. And let me just show you one picture at the end. So the gravitational wave can be a good tool for us to address questions like inflation and baryogenesis. So that's the exciting future awaiting us. So thank you very much.
Professor Hitoshi, I have to say you're one of the most amazing speakers I have ever seen. I really enjoyed your talk. Thank you so much.
Thank you. Thank you.
I am so sad that I was not able to be there to like laugh and comment things in person. Anyways, I have two questions. So let me change my speaker. So when you were talking about the idea of the initial condition, that you had the picture of the basically God starting the thing, what I understood from the discussion we had yesterday about why you need inflation is that if you inflate things very, very fast, you keep things from being in contact with each other, like the island example that you made. So actually that made me think that a fast inflation will preserve your initial conditions rather than erasing them. So do you have a comment on that, on what I'm interpreting wrong?
Yeah. So what we are talking about as asymmetry, as I mentioned, is the ratio of the difference between matter and antimatter over the number of photons. And that was supposed to be like 10 to the minus 9. Mm-hmm. The problem is that you can preserve the difference between matter and antimatter by inflation, but you would divide it by the number of photons that appear by turning the inflationary energy into thermal energy. So you create, and you end up creating huge number of photons relative to the asymmetry you preserved. And that's the big reset I mentioned.
I understand.
So that's why it gets totally diluted.
Yeah. The problem is the denominator, that it gets increasing if you do this. Instead, if you have a dynamic process that creates more antimatter than matter, the thing gets conserved as you increase.
Exactly.
That makes total sense. Thank you.
Right.
And my second question is, so you explain the idea that maybe the neutrinos are the superheroes. How do you create baryons like protons and stuff if I give you a bunch of neutrinos that violated that asymmetry?
Yeah, that's an excellent question. And that's the slide I actually did skip. So idea is the following. So in the early universe, and everybody heard of the Higgs boson, I believe, and Higgs boson is yet another kind of superconductivity. So at high temperature, it was not superconducting, and the electromagnetic field was in a thermal plasma. So even the W and Z field of the weak interaction was also massless and was fluctuating in a thermal plasma. And when you look at the Dirac equation, in the presence of this fluctuating W field, you all learn in quantum mechanics class that you are supposed to fill the negative energy states. You're supposed to keep the positive energy states open. And these energy levels are going up and down as the W field fluctuate in this thermal plasma. But once in a while, they go over a pretty large level fluctuation so that these negative energy states might actually pop up above zero. And this process is called electroweak anomaly in quantum field theory. But once this happens, you observe one positive energy state is now occupied. Then you say, aha, there is a particle now. So what happens here is that whatever fermions that will couple to W field, which means all the left-handed fermions of lepton doublet, which includes neutrino, and the quarks in 3 colors, change by the same unit. So you change baryon number by 1 unit because you have 3 quarks with each baryon number 1/3, and lepton number of neutrinos by the same amount. So if you start with a state where you have asymmetry in the lepton side, then using this process, you can turn the asymmetry of the lepton side to the baryon side, and they eventually reach a chemical equilibrium between the two. So initial lepton number gets transformed to the baryon number at the level of 35% or so. So even though the asymmetry you generate is actually asymmetry in neutrinos from this process, it turns out that that would automatically turn into the baryon asymmetry by this process known to exist in the standard model of particle physics.
Fantastic answer. Thank you so much.
Great question.
Sabia?
Yeah, hi. Although this was not mentioned in the talk, but I was just wondering that the different inflationary models that you showed, do they predict completely different reheating temperatures, or I mean, is there any way to distinguish them based on the reheating temperature?
Yeah, so one of the hopes of doing this experiment with Big Bang Observer and DeSigo was to actually get some idea on reheating temperature. Because if the reheating happens early, then inflation is already gone by the time you reach the scale of the small scale, the solar scale experiment.
Right.
But if reheating is low, you may still get the gravitational wave from inflation on this, short distance experiments, so that you get some idea on the reheating temperature.
And
but as
how
I said,
low you mean by low?
I actually forgot the number. Sorry, I have to look it up. I apologize.
Okay, that's okay. Okay.
But as I said, you need to have a bump in the level of the gravitational waves emitted from inflation if we actually have the chance of observing it at this kind of a human scale experiments. So the people these days don't think that it's very likely. But anyway, that's the only probe we can think of right now to say something about the reheating temperature.
I see. Thank you.
Okay. Next is Baja.
So how exactly we know that we don't have antimatter in the universe? For example, could we think that somewhere at some point we have some antimatter, but we don't have causality connection with this region, and probably we don't need any baryogenesis or something? Or it is experimentally excluded completely?
Yeah, that is also an excellent question. So what we can say is that within the observable universe, within 13.8 billion light years, there is no island of antimatter. Because what we know is that the galaxies actually colliding and merging all the time. If you have a galaxy made of antimatter, which undergoes a collision with a galaxy made of matter, then you will see huge sprays of gamma rays coming from that, and there's no sign of it. So we believe that to the extent we can observe, the entire universe is made of matter only, no antimatter. But as you said, if you go to way beyond that, in a different causally, in different patch of the universe, which is not causally connected with us, maybe there's another island universe made of antimatter over there. But to explain this, you have to, again, come up with some mechanism for it, because the stretch of universe we can observe today was causally disconnected in the early universe after the inflation was done. So how come you can create the same sign of the matter within the horizon we observe today? So that something needs to violate causality. And the idea people came up with is, okay, maybe we planted a particular scalar field which has a particular value at the time of the inflation. Inflation stretched that particular value to the entire horizon we observe today. And that sign of the scalar field eventually turned into a particular sign of the baryon asymmetry. You have to come up with a mechanism for it, so that we have a particular sign within the observable universe, but maybe a separate patch way over there elsewhere in the universe made of antimatter. So that kind of idea is called spontaneous baryogenesis. You can look it up. And it's not easy to come up with that kind of theory, but at least idea exists. But it's not free, as I said. You still need to come up with a mechanism for it. Yeah.
Thank you.
Okay. I'm sure there must be a question, particularly from younger people. Any questions?
I had a question, but I'm not too young, so.
I think you're young, so young-ish. Okay.
Come on, Kevin.
We're talking about 13.7 billion years. You're very young.
Thank you. My question has to do with the back on the plot where you're looking at the inflation models, and there's comparisons of the number of e-foldings, and I've always found that, I don't know, I would like to hear your take on the sort of 50 versus 60 versus what happened before, and if you have any comments on that?
Yeah, I don't have particular preference on these numbers, but I can tell you what people say about it. So there's one camp that says that in order to come up with a theory of inflation, which has rather flat potential to allow for this slowly rolling scalar field, that is kind of fine-tuned, and therefore it's not natural to expect a very long period of inflation where potential is flat, and therefore the e-folding is supposed to be probably minimum. So we are just lucky that we get e-folding of 50 or 60 by some accidental reasons. So that is the camp that prefers sort of as small e-folding as possible. Another camp says, well, there must be some kind of a theoretical formulation or some deep reason that the flat potential is supposed to come out of the theory, of some fundamental theory. And if you have that kind of theory, then flat potential is supposed to be natural. Then if you start from random location of the initial condition, then you are bound to have e-folding, which is huge, maybe 1 million. So if you are in that camp, you expect the e-folding to be very, very large, and we're only looking at the tail end of the inflation. So the reason why people argue about it is because of these two camps, thinking about how natural the inflation is from the point of view of the fundamental theory. And so hence all the arguments. Does that make sense?
Yeah, to some extent. So the camp for the short duration, do they believe that there is some sort of dynamical process that drives the potential into the proper state, or?
No, it's more like just a sheer luck. So the universe is created by string theory or something. And the string theory gives you all kinds of different universes. And each universe has different inflaton. Each universe has different laws of physics, different particle content, different forces. And in one patch of the solution to the string theory, you don't have inflation. In fact, in most patches, you don't have inflation. In some very lucky patches, then you actually find this flat potential, which does allow for inflation. So that's why in most universes, e-folding is 0. And by just pure accident and sheer luck, we happen to have e-folding as large as 50. So that's this camp of thinking.
Okay. All right, thank you.
Okay, let's see. By the way, what is a timeline of the light board experiment?
The launch is towards the end of this decade.
Okay.
27, 28.
Toby, may I ask a question?
Sure. You're young.
I had a question too after.
Okay,
so coming to the consistency between Big Bang nucleosynthesis or CMB for the ratio of baryons to photons. So you have there a very famous plot that of course looks very consistent, but has intrinsically this problem with lithium.
That's right.
And I've heard that many colleagues have tried to solve the problem, but it's extraordinarily elusive. So do you have any idea of what might be going on with this lithium anomaly?
I'm not expert on this, but my hunch is that it's probably an astrophysical issues. So the way people observe lithium-7 abundance is not in primordial gas, but in absorption lines in stars on the surface. And there's a big debate about how primordial the abundance of the lithium-7 is on the stellar surfaces. And you try to look for low metallicity stars to identify very old systems. But if there's any convection of the nuclear fusion happening at the core to the surface, then lithium-7 abundance would change as a course of the nuclear fusion process in the star. So what we are observing as a lithium-7 abundance may be partially destructed by the fusion process at the core. So that's one at least argument people make why the Big Bang nucleosynthesis theory and observation seems to be different from each other.
Thank you.
Laura?
Yeah, I was just wondering, since you mentioned the gravitational waves from the electroweak phase transition, right? So I was just wondering, what is your view of these from the point of view of complementarity? Do you think it's plausible or realistic at all to expect to get complementary informations from gravitational waves on the nature of the electroweak phase transition? By the time we'll have some more decent measurements from colliders, right?
Oh, well, yes, certainly. So I actually did not talk about electroweak phase transition. This is a sort of garden variety generic phase transition. But if you specifically look at the electroweak scale, which is like a 250 GeV, then this green peak would move over here so that it really does fall into the coverage of the LISA range.
Right.
So it is possible that the LISA would see stochastic gravitational waves coming from these bubble collisions at the electroweak scale. And as you know, the standard model actually doesn't lead to any phase transition whatsoever. It's a crossover. So you really need more complicated Higgs sector to make the first order phase transition possible. But nonetheless, it is possible. And in that case, of course, we also expect that the Higgs self-coupling to come out differently when you measure at the collider experiments. So that would be the complementarity.
Yes,
so collider would,
complementarity, because it's something that we cannot see at colliders, right?
Mm-hmm. Yep. So the gravitational wave would tell you about the nature of the phase transition being first order, and the collider experiment would measure the self-coupling of the Higgs boson that would show deviation from the standard model. Then you start getting, again, sort of fossils in the sense of archaeology that you seem to believe. Then you have something fundamentally different going on in terms of first order phase transition.
Right. That's exciting.
Yeah, absolutely.
Yeah.
Okay, let's see. By the way, while I'm waiting for other questions, so can you make a comment on the IOC, because we are looking at this Higgs related stuff. So because you're involved in the IOC, people ask me, but I'm just Japanese, so I don't know. So can you make a comment on the IOC project?
Yeah. So the IOC is actually gaining momentum these days. One of the reasons why there's momentum is the US government is actually getting very serious about it. And actually yesterday I gave a talk at the American Workshop Linear Collider right after the Dirac lecture, actually. And there was a representative from State Department giving a speech and showed really strong interest in this. So of course, US and Japan is allies and shared same values, democracy and intellectual property and all that. And so maintaining very strong scientific ties is something high on the agenda in the US government. So if Japan makes a commitment to build the machine, then basically State Department representative said, of course, US would work together on that. And Europe came up with their community planning this year, and they came up with a statement that the highest priority next generation collider will be Higgs factory, and IOC is a prime example of this. So basically 3 regions of the world have the common goal now. So that's why it's gaining momentum. So at least this is the hope that we are now at the stage of trying to propose a significant amount of funding at the level of few tens of millions of dollars from the Japanese government. And the budget request may well go into the government budget plan actually next round, which is next summer. And then we start a process called the pre-laboratory or preparatory laboratory to start into looking into the more detailed designs and site-specific fashion in the Kitakami Mountains, Japan, even at the level where you pave the road and where you actually bring the power lines and all these details starting next year. And that will be a 4-year process before the final approval of the IOC would happen. So we are not talking about decades. We are now talking about a few years to see any development in IOC. So that's getting very exciting, actually.
How about contribution from China? Are they going to their own plan, or they may join the?
Yeah, so what Chinese said is that they would like to be part of IOC, and they would like to make an in-kind contribution by building the superconducting carriers. And they also talked about their own project of building a circular machine, but they just missed the boat of the next 5-year plan in this, communist way of planning economics in China. So they missed the boat. So at least we know that will not happen the next 5 years. That's why they're showing more keen interest in being part of the IOC project.
Interesting. All right.
One short question.
Yes, go ahead.
First of all, Toshi, that's probably the finest 2 talks I've ever heard on cosmology. You did a great job.
Thank you so much.
I've got an off-the-wall question, just trying to put together pieces, and I haven't gone back and dug through the Sakharov conditions and so on and so forth. But in recalling the Penrose singularity theorem discussion associated with the prize and all that, for CP violation to occur, you're still assuming that CPT holds, right?
Yes.
But the Penrose theorem says that time can only go forward once inside a black hole into the center. You can't go back. And it's just a wild question, but is there any conceivable way that primordial black holes could influence baryogenesis by disrupting the processes or collecting some particles and not because of that?
Well, some people speculate about it. So if
Really?
you can come up with a theory where black holes can suck in antimatter, but not matter.
Exactly, that's the question.
Then you can create asymmetry.
Okay.
And it's not, I would say it's awfully difficult to come up with a theory of gravity that does that, because gravity doesn't distinguish matter from antimatter. That's the equivalence principle. So you have to come up with a very clever idea how black hole would preferentially suck in antimatter over matter. And I haven't seen anything plausible along that line, but people speculated. So that's worth thinking about.
Yeah, well, I won't waste more time, but those connections are interesting because time can only go forward toward the center. But thanks again for a great talk.
Okay, so maybe Laura, you can have it.
Yeah, I mean, we are at the end of this week and of this event that we organized for the Dirac lectures, and we couldn't have a better ending. This was a great couple of lectures that we had, and we thank Hitoshi so much for having agreed to give part of his time to this event. And thank you to everybody who participated, because that's part of the success of this event, with your presence, your questions, your enthusiasm. Thank you so much, and goodbye to everybody now.
Thank you.
Thank you very much.
Bye.
Thank you.
Thank you.
Great job.